present our research on small diameter vasculature detection with coherent flow power Doppler imaging. I'll begin by talking about the principles of coherent flow power Doppler or CFPD imaging, and then the performance of CFPD in small diameter vessel detection will be demonstrated with both linear and nonlinear simulations, as well as a phantom experiment. So CFPD imaging is a flow detection method based on the spatial coherence of backscattered waves from blood. This slide presents a short introduction to spatial coherence imaging in medical ultrasound. Spatial coherence measures the correlation of waves in two different lateral spatial locations. It can be calculated as normalized cross-correlation between signals received on two transducer elements. If we plot the spatial coherence as a function of the spacing between these two elements, diffuse target will produce a curve that is the same as the normalized autocorrelation function of transmit aperture function as predicted by Vansittart-Zernike theorem. For example, if we have a rectangular aperture, the curve would be a triangle, as shown in the blue curve in here. If the transducer element only receives thermal noise, the resulting spatial coherence curve would be a delta function centered at 0, as shown in the red curve in here, because thermal noise is spatially incoherent. If the signal on the transducer elements is a combination of diffuse scatter signal and the thermal noise, the resulting curve would be approximately the addition of the delta function and the triangle function, as shown in the yellow curve in here. Using the differences in the spatial coherence properties of different targets, we can form images. One method is called short-leg spatial coherence, or SSCP beamforming. It basically calculates the sum of the spatial coherence values up to a certain leg. For example, 13% of the transmit aperture size. In previous studies, SSCP beamforming has been shown to produce images that look similar to those of B-mode, but have better separation of spatially incoherent noise, including thermal noise and reverberation clutter. CFPD applies SSCP beamforming to flow detection. It begins with the same acquisition sequence as conventional power Doppler imaging. For example, we can use focus transmit, in which the transmit beam is focused in one lateral location of the sample. Multiple acquisitions are taken and a fixed pulse repetition rate. The data are then time delayed and high-pass filtered to remove stationary signal. Then the SSCP beamformer is applied to extract spatial coherence information out of the filter data. A power estimator, for example, the lupus estimator, can be then applied to produce one A line in the final Doppler image. If we scan the sample with the beam and repeat the process, we can build a Doppler image with CFPD. In previous studies, it has been shown to have higher sensitivity than conventional power Doppler imaging in slow flow detection and the flow detection in low signal-to-noise ratio environment. In this study, we would like to demonstrate that CFPD is flexible because it uses time-delayed RF channel data, so it's not dependent on a specific imaging sequence. For example, we can use focus transmit sequence or a plane wave transmit synthetic aperture sequence. In addition, we would also like to show the performance of CFPD in small vessel detection. So linear and nonlinear simulations are done to study the performance of CFPD under different environments, and we have a phantom experiment. In the linear simulations, we used field 2 to simulate a homogeneous phantom with a vessel centered at 3 or 3.7 centimeter depth. The vessel diameter varies from 0.2 to 2 millimeters. Blood signal is simulated with scatterers that have scattering amplitude that are 16 dB weaker than stationary tissue. And the scatterers inside the vessel move with a parabolic velocity profile with a 5 millimeter per second maximum at the center. Then we will use imaging sequences to image a cross-section of the vessel. Those sequences simulate a transducer that will be later used in our experimental studies, which is Verisonic's L12-3V transducer with 0.2 millimeter pitch and 128 elements. The center frequency is 7.5 megahertz. Two sequences will be used in the simulation. One is the focus transmit sequence with 3 centimeter focus and f2 setting. The second one is play wave transmit synthetic aperture sequence with 17 transmit angles covering plus minus 8 degrees. White noise will be added to the received data to simulate thermal noise. Here are some images produced with the focus transmit simulation. In this simulation, a 1.8 diameter vessel is used and the negative 20 dB channel noise is added relative to blood signal. The CFPD image is on the left and the PD image is on the right. The display range is 13 dB. The white circle here indicates the location and the size of the actual vessel. As we can see, in this setting, PD image results in quite high background noise. We can reduce the background noise by changing the display range. For example, if we change the display dynamic range from 13 dB to 20 dB, we can get rid of most of the background noise. However, the vessel in this case would appear to be fragmented in the Power Doppler image. If we plot the axial cross-section of the images, here is the result. The blue line shows Power Doppler image and the red line shows the CFPD results. We can see from this graph that the background noise level in CFPD is around 13 dB lower than that of Power Doppler. In addition, the vessel size is preserved in the CFPD results, but it's broken up in the PD image. Quantitative measurement of image signal-to-noise ratio is done. The figure on the left displays the Doppler image signal-to-noise ratio as a function of the channel signal-to-noise ratio. We can see that in most cases, CFPD results in an improvement in Doppler image signal-to-noise ratio, except when the noise is really high and both methods cannot detect the vessel. The improvement is around 5 to 25 dB, or 13 dB in this case. The figure on the right displays the image signal-to-noise ratio as a function of vessel sizes when the channel signal-to-noise ratio is 20 dB. We can see that the improvement of CFPD over PD is quite stable with vessel sizes, except when it's really low and below the resolution of the system. Here are some more results from the simulation with plane wave transmit synthetic aperture sequences. It confirms the conclusion of the previous slides. When the channel noise level is low, both methods can display the vessel, but the vessel in the PD image is fragmented. When the background noise level increases, the background noise in the image of PD increases much faster than those of CFPD. Quantitative measurement confirms the conclusion. So we can say that CFPD is less susceptible to thermal noise than conventional Power Doppler imaging. Full-wave simulations are conducted to study the performance of both methods in the presence of reverberation clutter. Full-wave simulation tool is a customized tool to simulate wave propagation through inhomogeneous media. In the simulation, we use the focus transmit sequence, and the human abdominal model is placed above the vessel to generate reverberation clutter. The flow velocity is 4.3 millimeter per second, and we added negative 20 dB noise to the received data. Here are the results. So in the CFPD image, we can see that the vessel has much better defined boundary than the PD image. In addition, the PD image shows scattered noise inside tissue where there is no blood. So the results suggest that CFPD is less susceptible to reverberation noise than PD. And that's because reverberation clutter is also especially incoherent noise. Experiment is done with the flow phantom, which has a 2 millimeter diameter vessel. This is the smallest we could find. And the velocity was controlled to be 10 millimeter per second, and the vessel is located at 12 millimeter depth in the fetal. For imaging, we use a varosonic scanner with L12-3V transducer. The center frequency is 7.8 megahertz, and the pulse repetition rate is 500 hertz. Plane wave transmit synthetic aperture sequence is used, and it has the same setting as used in the simulations. So I'd like to mention that this is a relatively easy imaging case. The flow velocity is not very low, and the vessel is shallow. But even in this case, CFPD can result in better detection of the vessel. We can see that it reduced the background noise that is seen in PT image, and the vessel appears to be better defined than the Power Doppler image. The figure below here displays the center cross-section of the vessel in both images. We can see that CFPD reduces the background noise level by about 20%. In conclusion, the CFPD method detects flow from the spatial coherence of blood signal and improves the signal-to-noise ratio compared to Power Doppler imaging. The improvement is dependent upon the channel signal-to-noise ratio, and in some cases, the vessel diameter, and the improvement can be as high as 13 dB. CFPD results in a smoother vessel profile compared to Power Doppler image when they are used to detect small vessels. Therefore, CFPD shows promise in improving small diameter vessel detection. Lastly, I'd like to thank our collaborators and our funding sources, and I welcome your